Hello, and welcome to episode 7 of our series on nuclear physics for grade 12 physics. In this video, we're going to take a look at fusion, which is the last nuclear reaction we're going to look at. Fusion is the power source behind the sun. This is how the sun produces all of its energy, and this is how most of the energy that we have access to on Earth is provided. Chemical energy from plants that we eat, or energy from fossil fuels that we burn, at one point was energy released by fusion in the sun. So almost all of the energy that we have access to at one point was coming from fusion in the sun. Now, fusion is the process by which light elements such as hydrogen and helium are combined to create heavier and heavier elements. This only works for light elements. So let's take a look at a couple examples. The most basic fusion reaction is when we take two hydrogen nuclei and combine them to create deuterium. So this first reaction here, I have a hydrogen nuclei colliding with another hydrogen nuclei, which creates deuterium, or hydrogen 2, plus a positron and a neutrino. This is the first step. So what's going on is I have two hydrogen nuclei, which are just protons, colliding with each other. You may remember from grade 9 science, these are both positively charged, so they want to repel each other. In order to get two hydrogen nuclei to collide, or to get close enough so that the strong nuclear force takes over, you need to have these moving very fast. In fact, their kinetic energy needs to be greater than the potential energy barrier called the Coulomb barrier. We can figure out how much kinetic energy that is, but these need to be moving very quickly. If you remember from chemistry, when we have particles moving very quickly, very quickly, we have high temperature. So in order to have hydrogen fusion happen, we need a very high temperature on the order of millions of degrees Kelvin in order to get these particles to have enough energy to collide and combine. So the first step in our proton-proton fusion is to take two hydrogen nuclei, combine them into a deuterium nuclei, which is an isotope of hydrogen. One of these protons turns into a neutron, and similarly to beta-positive decay, releases a positron and a neutrino. This next here, this deuterium nuclei, can then combine with another hydrogen nuclei. This is a possible second step in this process where you might get, if you have this happen, you'll end up with helium-3. This helium-3 nuclei is very excited because it has a lot of energy in there from this collision, which means that it releases that energy in the form of a gamma ray. Now, the helium-3 nucleus is not stable. In order to make that stable helium-4, it might collide with another hydrogen nuclei. If that helium-3 nuclei collides with another hydrogen nuclei, we end up with, similarly, helium-4. That proton turns into a neutron, and we release a positron and a neutrino, and we end up with helium-4 as our product. So to go from stable hydrogen to stable helium, we need several steps. Now, this is not the only possible chain of fusion reactions. There are other ones. This is not even the only possible proton-proton fusion chain. However, this is an example of how this works. There's often intermediate steps. If I want to go from helium-4 up to lithium, which might be lithium-6 or lithium-7, then I end up with needing to have more collisions to create heavier and heavier elements. Now, if I go and look at our binding energy chart here that we have from our binding energy per nucleon and the number of nucleons, What I've got here is I've got hydrogen and helium way over on the left side of this graph. To go from hydrogen to helium, I need to move to the right on this graph. Remember, in order to release energy, I need to be moving up. So in other words, fusion releases energy when we are moving up and right on the graph. If I take a look, going from hydrogen 1 to helium 4 is quite a lot of energy that is released in this process. This here means that we have a lot of energy that's released when I fuse hydrogen into helium. Now, if I look at iron here, iron is the highest point on this graph, which means that I can only release energy up to iron. I cannot fuse iron or anything heavier than iron and end up releasing energy. That will actually consume energy instead. What this means is that in stars like our sun, they will fuse hydrogen into helium, into lithium, and on and on and on, but they will not be able to fuse anything heavier than iron. In order to fuse things heavier than iron, you need a huge amount of energy input, which is typically only found in supernovas or another process called neutron star mergers. Both of those release enormous amounts of energy. You may realize that we see things heavier than iron on Earth very commonly, such as uranium, or gold, or lead, or anything heavier than iron here that you see cannot have been produced by the same process. That element must be produced in either a neutron star merger or a supernova, which is really cool because it means that the gold in your jewelry, for example, the gold in my wedding ring, was produced in the explosion of a star or the collision of neutron stars, which is really, really cool. Now, fusion is also a possible candidate for producing energy or creating electricity on Earth. This is another very promising solution, very promising way that we could create energy in a way that produces zero greenhouse gases. This is a really good option for us, but despite the hype of fusion, there are some challenges with it. So far, we think we are going to need very large reactors in order to produce energy from fusion. There is currently an experiment in the south of France called ITER, or ITER, that is looking at trying to produce fusion by 2025 or 2030. Hopefully, they will be able to have fusion happen and produce more energy than it consumes. Remember, you need to get it very hot, and you need to contain this very, very hot magnetically charged gas. So there's a lot of challenges with that. We're going to take a look at some of the challenges with fusion, and we're going to take a look at possible solutions for fission as well for generating power a little bit later in this course. However, I hope that you have a great day. I hope that you've enjoyed this video, and ladies and gentlemen, please don't forget to like and subscribe.